Hi, IB Physics kids. Mr. Tima here. I'm going to talk to you a little bit about tension today. We feel a lot of tension right now with everything going on, but that's okay. This is a little bit, you probably all played tug of war and you felt tension. You know what tension is. You probably stretched a rubber band, things like that. Okay, but tension is just a type of force. Okay. Created on a rope, string, or cable when force is applied to it. It's kind of the reaction force of us pulling on a rope, directed away from the force but parallel to the rope. So, for example, in outer space, there would still be tension. Even though there's really no air resistance or gravity or anything like that, we'd still feel tension. If you were to go pull on a spacecraft, okay, or some kind of object by a rope, you would still feel that tension force because Newton's first law of inertia says for us to get this ball moving or this craft or something out here, we would need to pull on it. And that tension is the reaction force to it. So, where in this force is there tension? Okay. Well, you're probably thinking to yourself, it's either on the body or on the ropes. So, what do you think? Take a guess. Well, if you said the ropes, you're right. The body itself, because of gravity, that's the vector pointing down. And then we have tension on each of the ropes. And if we assume that both of these angles or that this is parallel, okay, we would assume that these tension forces are equal, but they would add up to counteract the force of gravity. So, for example, if we look at 1,000 Newton block, and remember, Newton means we've already done F equals ma. So this would really be a 100 kilogram box because we'd multiply it by gravity. We're just going to use 10 for gravity. So this would really be a 100 kilogram box, but we say 100 newtons because we're talking about weight. We need a force down. Okay, draw the free body diagram, then draw the net equation, and then calculate the tension on each cable. Well, here we go. So if you were to draw the free body diagram or the force diagram, what would that look like? Well, it should look very similar to that of the guy on the ropes. You should have a force down due to gravity, negative, and then our tension force coming up. And both of these vectors would add up to equal the force of gravity. Here's our net equation. All right. The sigma force net, but the net force would be equal to the tension of A plus the tension of B minus the downward force due to gravity. And all that should equal zero. If it didn't equal zero, then the box would be pulled up. Let's say if it was positive, if it was negative, that means the box or the sign or whatever would be falling down. And then the tension on each is easy. Since these are parallel or perpendicular to the box, but parallel to each other, it's just simple. If it's a 1,000 Newton box, then we'd assume that there's 500 Newtons on each, which is why when we hang something, right, we all know that if we put one bolt in the wall to hang a picture, that one bolt might get pulled out. We put two, less likely. Put three, very unlikely something's going to fall out. Or if you've ever hung something like in the garage or the basement or something like that, the more things we hang, the less likely it's going to break because that tension or that force is being distributed across all of them. Right? What would be the tension on each cable if there is now three? Well, 1,000 newtons. We'd do what? We'd split it three ways. So our answer would be about 333.3 continuing newtons, or we just say 333 newtons per each. Okay? But they would all add up. That's pretty easy when they're straight up and down. Now here's some force diagrams just so you can see. Right here, would these pulleys be moving? If I just let them go at this position, would they move? The answer is no. This one would not move. Look at the tension. Tension, down, down. They're all equal. The size of those arrows are all equal. So they wouldn't move. Now, if I move this guy up here, this one would drop down, right? But if I let it go, they still wouldn't move because they're all equal to each other. They're all happy. Inertia still plays a part here. Now, if I look at this one, would they move? And look, these are the force arrows that correspond to these. And the answer is yes. The answer is yes. The answer is obviously with this vector, you can see the tensions are equal, but the force of gravity down on M1 is much less than the force of gravity down by M2, which means M2 must have a much larger mass. So if we let this go, no matter where we would let it go, M2 would go down and M1 would go up. Just another way to look at it in those pictures. All right, so what's going to happen here is you can watch the rest of these notes, but you're going to have to, there will be um, a link to this video. This video is the first of 3 videos. Okay, at the end of each video, it will ask you to make a guess and see if you're right. Okay, either way, if you're right or wrong, it's still going to show you the correct answer. But it's pretty cool. It's about the slinky drop. And I will tell you, a lot of kids, when you first see it, you don't get it right. So make sure you look at this video. Again, it's like a 4-minute video and then 2 1-minute videos. Okay, very simple. But this is a separate thing. You'll find it in your notes folder. Okay, it'll be the slinky drop video. But the reason I'm not putting it on here is because you actually have to choose, um, which one you want to guess, and it'll kind of explain why or why not you're right. Table experiment. Now, we would usually do this in class, and we'll talk about this in class if you're in class. But the idea is that at home, you can even do this if you have 2 very stable objects. If you've ever done a dip, if you've ever done like a dip, which is where you put your arms on a table and you go straight down to parallel where your elbows are bent and then you push back up. You've probably heard of that, a dip. Well, if you do it where you're dropping straight down and your arms are pretty much straight up and down, a lot of you can do a lot of those reps. But as you widen those tables or widen those objects, it gets much harder, exponentially harder. Okay. And this is why, because we tend to have our signs hung at an angle. Okay. We tend to not hang things straight down at times. So, what would the tension be on the cables now? Well, let's just pretend this 1,000 Newton or 100 kilogram box times by gravity would be 1,000 Newtons. If this cable is not really there, okay, this black cable's not really there. We're really talking about these brown cables right here. I just put it there as reference. If this black cable was just there and the brown ones weren't there, how much tension would be on this black cable? The answer is 1,000 Newtons. Okay, if there was one cable, it would counteract. Okay, well, how much tension is on each of these now? Well, it's not 500. Before it was 500 because those brown ones would be straight up and straight down. But these angles are important. We have the angle off of the black one, but we're going to talk about that. So how do we solve this? Well, we have to kind of pretend that that box is still down here, okay? But what we want to do here, is we want to make sure that we understand that that black cable doesn't really exist. It's just to kind of show you that, all right? But what we need to understand is that if our box is still down here, okay, all right, and let's just say, again, that's 1,000 Newtons. You get 1,000 in there, okay? We have to pretend that there's 2 imaginary straight up and down ones over here in the Y. And we said that if they were straight up and down, they would be 500. So this side, if you will, is 500. If the box was big enough to reach out here, these are imaginary, but we know that these would be 500 out here, okay? And we did that on the other box. That was easy when they're straight up and down. But if we pretend now, we know that this is basically a right triangle. Again, oh my goodness, we're all back to those right triangles. It's a horrible right triangle, but stay with it. All right. Now the angle here was 40. All right. The angle of that one is 40. So if we think of it as a right triangle, we now know that this angle is 50 degrees. Okay. And then this one's 50 degrees. And again, these could be different angles. These could be different angles, but I'm just making it easy for you right now as an example. These are 50 degrees right here. Okay? Now, how are we going to calculate the tension? Some of you are probably jumping out of your skin right now going, well, that's easy. Because it's a right triangle, we know the opposite side over here. We know the opposite, and the tension that we're looking for is really just equal to the hypotenuse. I'm just going to put HY for well, I'll put HYP. Okay, is just equal to the hypotenuse. So how are we going to do that? Well, opposite and hypotenuse, we should be thinking sine. Okay, we should be thinking a sine. The sine of 50. Remember, not 40. We're not using 40. We're using 50 because remember, 40 is up here. Okay, we want the angle inside the triangle is equal to the opposite, which is 500. Okay, which is equal to 500. All right, over the hypotenuse. And if you calculate that, what do you think? Is that number going to be greater than 500? Or is it going to be less than 500? Well, if you were paying attention when I talked about the table, since now we're at an angle and we're not straight up and down, the tension here should be greater than 500. The tension here should be greater than 500. I want to say that it's around 600 and some. Okay. And if you add those together, now the total is around 1200 plus newtons of tension instead of just regular old 1000, which means there's actually more tension on these ropes as we spread the angle. Technically, it is impossible to hang a sign at 180 degrees. Okay. Because if you do the sine of 90, you know that that's zero or it can't happen. It's undefined. You can never hang a sign like this because if our force of gravity is down, there's nothing up here to counteract that force. It's parallel or perpendicular. Sorry, not parallel, perpendicular, which means will always sag. If you ever tried to hang a sign like this, it will always sag down. It will never be straight across. Threw a lot at you there. You're going to have to work those practice problems and things like that, and we'll be good to go on that. But hopefully you can see this. To be honest, this is really one of the only tension problems you have to learn. So as long as you can learn how to do this tension problem like this, it's basically the same procedure over and over again. And we'll be doing a lab later on about it and everything like that. So again, if you can just master this concept of knowing how to do this kind of problem, you are going to be set with tension problems. Unlike, kind of like in projectile motion, we had multiple problems, multiple equations. What's really nice about this is in tension, we pretty much have one type of problem. So you should be ready to go on that. All right. So, for example, just a real thing quick, as you notice, straight up and down, the tensions, let's just say it was 20 on each rope. Well, now as we start to spread it, the tension goes to 30 to each rope, and then look at that. So, exponentially increases. So, it increases exponentially. Very important. So, again, here's my guy. He's doing what's called the iron cross. Okay. And again, technically, this is impossible. If you ever look at their arms, okay, they never are completely are perpendicular, okay, because the force of the weight going down is always going to be greater than the force that we can create perpendicular because there's nothing really in the parallel direction straight up to hold them up. So they tend to sag a little bit. But again, for example, pretty impressive, right? All right. So obviously, you have some book problems. You have a worksheet that you need to work through. Make sure that you also watch the video. Make sure you watch the video so that way you're good to go. And make sure that we're going to try to do a tension lab as well in class. Again, threw a lot at you. Hopefully, you enjoyed these notes and have a great day.